So the only thing we can see you and your presentation, and that's enough. So
maybe sometimes I'm offline, so I don't notice that.
you know what?
If I'm offline. So,
I. What do you mean?
oh, the other day like internet, no, I'm offline, so I don't know.
Okay.
Hi, Cecil.
So
How are you doing?
I realized I made a mistake. I told Ziming Wu that the talk is going to start by 12:30.
Ah,
So the Chinese student might join a little bit later, but it's okay. So, wow, okay. So good morning, everyone. So first, I would like to thank all the speakers in the previous session in Spanish. So actually, I have to say all these are all the organizational work has been done by Angel. So okay, you can just put my name. So for this session, our first speaker is XiaoxinZhang. So he finished his education in Harding University, and he came to Spain in 2005. And now he's a professor in Almaden, in the University of Castilla-La Mancha. So he's going to speak about the work he has been done with us. Go ahead, Xiaoxin.
Okay, thank you. So the title of my presentation is Correct Velocities in Steel Fiber Reinforced Concrete at a wide range of loading rates. Okay, as Rena mentioned, my name is Xiaoxin. So the co-authors are Gonzalo Ruiz and Adris Elasin. So the contents are as follows: introduction, experimental procedure, experimental result and the discussion, and finally summary. Introduction, as mentioned by Professor Jaime Galvez. Okay, so I'm talking about the steel fiber reinforced concrete. So it's concrete made of hydraulic cements containing fine or fine and coarse aggregate and discontinuous discrete steel. And also, of course, steel fiber reinforced concrete is widely used in the constructional field, such as hydraulic structures, airport, highway paving and overlays, industrial floors, and the thin shell structure. For example, in the photo in the right side, I mean, the bridge deck was made of steel fiber reinforced concrete. The depth is around 25 centimeters. So why dynamic behavior? Because we are always studying like quasi-static fracture behavior of fiber reinforced concrete, but why we need to study dynamic behavior? So here, okay, the response of concrete and the concrete structures under dynamic loading is of interest in a variety of civilian and military applications. So understanding the response of concrete and the concrete structures to impact or explosive loading is important for the successful destruction of military targets and for the effective protection of defense structures. For example, like explosive loading. I mean, this topic was mentioned by Professor David Sendon, just the presentation previous. So why we need to study? I mean, here I just want to show some examples. For example, like this photo shows the protective shells of nuclear power plants are expected to survive the impact loading of an incoming missile or other sources. Okay. So the next example, design consideration is also given to the possibility of ship impact on gravitated platforms for oil extraction in the sea. I think this we are familiar with that, okay? Like airport runways must withstand repeated dynamic loads due to aircraft or plane taking off and landing. So I think everyone knows these structures or these photos. So dynamic loading on concrete structures like, okay, so like a plane impact, also like earthquake, ocean waves are also interesting. So this is why we need to study the dynamic behavior of concrete and the concrete structures. So characterization of the behavior of concrete and the concrete structures under impact or impulsive loading is a prerequisite for the design and the analysis of these structures. So this slide just shows some basic information on fracture mechanics. Normally, fracture mechanics, it consists, okay, it concludes correct initiation, correct propagation, and also correct arrest. Of course, if the thickness of structure is not enough, maybe you just have correct initiation and correct propagation. So correct arrest, you cannot find it. So in this topic, okay, so I want to concentrate on the second item, like the right side lower down. So correct propagation means the velocity of correct propagation. So regarding the correct velocity or correct propagation velocity, so there are several methods as shows in this slide: high-speed video camera, digital image correlation, also it's DIC, acoustic emission, and also strain gauge. So in the lower, I listed 4 papers related with this topic. So regarding the high-speed video camera and the digital image correlation, so recently we have published several papers on this topic. But in this presentation, I want to concentrate on by using strain gauge to study the loading rate effect on the correct velocity in steel fiber reinforced concrete. The second one, experimental procedure. So first, material characterization. The second, 3-point bending fracture test. So here, 2 typical devices were adopted. The first one is a servo hydraulic testing machine. So the loading rate or loading velocity from 10 to minus 3 millimeter per second to 1 millimeter per second. So we can call it a low loading rates. The other one is drop weight impact machine. So this machine, I think we designed this machine like almost 20 years ago, okay? Also, it was the first impact machine in Spain for study dynamic fracture behavior of concrete and concrete structures. So the loading rate from 100 millimeter to 1 meter per second. So we call it high loading rates. Material characterization. So this table shows the mixed proportion by weight and also hooked end steel fibers were used in this research. The length of fiber is 50 millimeter. The diameter is 0.75 millimeter. Aspect ratio is 67. The volume ratio is 0.83%, corresponding to 64.5 kilogram per cubic meter. Basic mechanical properties. We prepared cylinder specimens, so we just follow the standard ASTM C39 and C469. So we get the basic mechanical properties like a compressive strength. So the mean value is 92 megapascal, elastic modulus 35 gigapascal, Poisson's ratio 0.18. Of course, the density is not exactly mechanical properties. 3-point bending fracture test. So the dimensions of the beam follows the recommendation of RILAM TC 162 TDF. So the section is 150 millimeter times 150 millimeter. The total length is 700 millimeter. So in fact, the weight of the specimen is around 40 kilogram. It's not that convenient to move it in the lab. So we bonded 5 strain gauges on the surface of the specimen. So SG01, okay, so the right figure, SG01, SG02, SG03, SG04. And also the 5th strain gauge, SG05, we bonded exactly at the notch tip of the beam. Why? So just we want to use this strain gauge to get the strain rate of the test. And also we notice this figure from the figure. Okay, so we bond the strain gauge. It's 20 millimeter offline the center. Why? So we, from the photo below, right below, so we can say, in fact, the crack path is not exactly the straight. It's in fact is a kind of like a curve. So this is why we want to avoid the crack pass through the strain gauge. from SG01 to SG04. So this is why we put or we leave like 20 millimeter from the center. Low loading rate, as mentioned before, so we use a servo hydraulic testing machine. So we do the test. So from the photo is very clear. Okay, we have two supports, and also we use LVDT to measure CMOD, and also like a data acquisition system also is called DAS. So we use MGC Plus, of course, laptop. So the three loading rates from 3.33 times 10 to minus 3 millimeter per second, 0.1 millimeter per second. Okay, and also 3.33 millimeter per second. So this is a video shows the test at a loading rate of 3.33 millimeter per second. Okay, so now from this video is very clear. So from this photo now, so we use LVDT to measure CMOD, okay, directly. So we see the video and okay, this is a rate sensitive test. Okay, the loading rate is 3.33 millimeter per second. Low loading rate. And also we have conducted several tests on high loading rates. So this is a drop weight impacted machine. So we designed it like almost 20 years ago. So the theory is very simple. So the hammer, okay, the hammer weight is 120.6 kilogram. So the drop height is 40 millimeter, corresponding to 8.85 times 10 to 2 millimeter per second, 160 millimeter, corresponding to 1.77 meter per second. So the last one, 360 millimeter, corresponding to 2.66 meter per second. Of course, this is a kind of impact test. So also here also shows the video how the test is. Okay. Okay, now it's very clear. The test is very fast. The test is over. So for this device, impact device, so how we know the impact force, also the reaction force. So in fact, we bonded or we used 3 force sensors, piezoelectric sensors. And also, for example, like the impact force sensor. So here, the maximum is 178 kilonewton. So now, like almost 5 years ago, we updated this device, so the maximum load now is double. For getting the loading point displacement, we use an accelerometer bonded on the upper surface of the hammer. So the maximum acceleration is 1000 G, okay? So for the reaction force, from the support, so the maximum is 89 kilonewton. This is the data acquisition system. Of course, it's complicated. So we have used 3 oscilloscopes and also signal conditioner. Here, signal conditioner, why we use it? Just because the force sensors and the accelerometers need constant circuit. In fact, this signal conditioner will provide constant circuit. And also, strain amplifier is used. Why? Just because the signal from the strain gauge is very weak. So we need to amplify the signal. So this is why we use this strain amplifier, of course, finally. So for analyzing the data, we need to use the computer. Okay, experimental result and the discussion. So the first one, data effects on the failure pattern and the peak loads. So in this slide, I show 6 photos. The lower, okay, for the low loading rates, from 3.33 times 10 to minus 3 millimeter per second. So we call it, and also is quasi-static loading conditions. Later 0.1 millimeter per second and also 3.33 millimeter per second. So in fact, from this lower photos, is very clear. So we look at the correct path. In fact, it's not that straight. Okay. So compared with the upper photos, so corresponding to impact loading rates, so from 8.85 times 10 to 2 millimeter per second, okay, drop height is 40 millimeter. So later 1.77 meter per second. The last one is 2.66 meter per second. So the upper line photos, I mean the correct path is quite straight. So we can consider, okay, the correct like a person. So he can think under low loading rates, the correct has enough time to think the correct path. Okay, he can choose. But under impact loading conditions, the correct doesn't have enough time to think. It's a little like this Sunday, so we will have Fiesta de San Fermin. Okay, so if after you there is a bull, so of course your idea is very simple. I should run fast, no more. So I think it's a little like the impact loading conditions. Okay, just because the velocity is high, so you don't have enough time to think. Of course, the correct path is straight. This slide shows the load versus time under impact loading conditions. So here we have two lines, two curves, black curve and also blue curve. Blue curve is corresponding to reaction force from the supports. The black curve is corresponding to the impact curve from the impact force sensors. Of course, just because the depth of specimen is 150 millimeter, of course, you have a kind of delay, like 248 microseconds, just because the stress wave needs some time from the impact point to the support point. By the way, I mean, this photo or this slide shows the drop height 360 millimeter. The corresponding loading rate is 2.66 meter per second. So this slide shows the reaction force versus loading point displacement for 6 loading rates, from quasi-static loading rates to impact loading rates, or from low loading rates to high loading rates. So it's very clear. So the rate sensitive for the peak loads is very clear. For example, under quasi-static loading conditions, maybe around 30, 35 kilonewton, while for the impact loading rates, it almost reached 200 kilonewton. Second, the rate effects on the crack initiation strain rates and the crack velocities. So here shows the SG05 strain gauge 5, just bonded at the notch tip, okay? So corresponding to the loading rate 0.1 millimeter per second. So we just make a zoom because this is the whole history of the strain gauge 05. So we make a zoom, so like this. So how we get the strain rate, because this is strain, so the slope is the strain rate. Okay, so strain divided by time, so we will get the strain rate epsilon dot. So of course we will get 6 different loading rates. What's the corresponding strain rate? So this slide or this figure shows the crack initiation strain rate versus loading rate. In fact, I didn't mention it before, like the size of strain gauge. In fact, the strain gauge is 6 millimeter in length and also 2.8 millimeter in the width. So from this figure, it shows clear. So strain rate, low loading rates, the relation is almost linear, while it reach high loading rates, reach the last 2 impact loading rates, the strain rate is almost constant or almost constant. So this slide shows under impact loading conditions, the signal from SG01, strain gauge 1, strain gauge 2, strain gauge 3, strain gauge 4. So the color like, okay, black, red, green, and also blue. The loading rate is 1.77 meter per second. Drop height of hammer 160 millimeter. So now we know the distance between strain gauge is 25 millimeter. So the peak load, the peak signal here, okay. So it means the crack just pass through the strain gauge. For example, this one, strain gauge 1, okay. Strain gauge 2, the crack passes strain gauge 2, the crack passes through gauge 3, or passes, not exactly through the strain gauge because we have 20 millimeter offside the center. Okay, the blue one. So we know the distance 25 millimeter, and also we know the time interval. Of course, we can calculate the average crack velocity between each period. So on the low loading rates, so according to the theory I mentioned before, so we just draw a figure like main crack extension. So like the black curve here, or like also black square. So the time we know, okay, each strain gauge, we know the distance or interval between different strain gauges, and also we know the distance here, so we can get the average crack velocity, for example, from strain gauge 1 to gauge 2. So for quasi-static loading conditions, so it's 5.8 times 10 to minus 4 meter per second, okay? The next one is 4.5 times 10 to minus 4 millimeter per second, of course, meter per second, sorry. The next one is 6.2 times 10 to minus 4 meter per second. So under quasi-static loading conditions, so it's clear, okay, the crack propagation velocity is almost constant. Look at the order of magnitude, of course, not exactly 5.8, 5.8, 5.8. No. It's just a little variation, okay, but the order is constant. So for another 0.1 millimeter per second, okay, the first period is 1.8 times 10 to minus 1 meter per second, while the second one is 7.3 or 7.7 times 10 to minus 3 meter per second, okay? The next one is 6.6 times 10 to minus 3 meter per second. So it means for the rate sensitive loading conditions, the crack initially propagates in a higher velocity, and later the velocity decreases. The blue one shows the similar tendency, okay, from 4.6 meter per second to 0.16, 0.23 meter per second. Okay, this is the phenomenon on the low loading rates. Similar on the high loading rates, so under impact loading conditions. So we use the same method, so get the different velocities. Okay, for example, 0.885 meter per second. Okay, because if I want to say millimeter per second, too many letters. So here from 5.7, 570 meter per second. Okay, decrease to 180 meter per second, and also 250 meter per second. While this blue one, okay, on the highest loading rate, so initial part 6.9 times 10 to 2 meter per second, 6.9 times 10 to 2 meter per second. The last one is 3.4 times 10 to 2 meter per second. So it means on the highest loading rate, the initial crack velocity is almost constant, okay? 69 or 6.9 times 10 to 2 meter per second, or 690 meter per second. So this figure just shows on the 6 loading rates, the crack velocity, okay, corresponding to loading rates. Okay, I just want to go to the summary. Summary, first one, loading rate, correct initiation strain rate. For example, loading rates, we have conducted a test from 10 to minus 3 to 10 to 3 millimeter per second. It covers 6 orders in magnitude. While for the correct initiation strain rate, so from 10 to minus 6 to 10 per second, I mean, it covers 7 orders in magnitude. Under quasi-static loading conditions, correct velocity almost constant. 10 to minus 4 at the 10 to minus 4 meter per second. Low loading rates 0.1 and 3.33 millimeter per second may correct advances with decreasing velocity. So on the high loading rates, I mean the early stage velocity, I mean the first or the second period, almost constant at 600 meter per second.